Hey, Yalimada Anwar. Can you hear me?
All right. Yalimada everyone. Thank you for joining. So today we will be talking about, NLP conversations, conversational AI. My name is Sahir Karani. I am a software engineer at Amazon Prime Video. I'm also the IPN software engineering community manager. So you've probably seen me, say some things in the Slack channel. Today we'll be hearing, Salim talk about modern NLP technologies. Before we begin, I just want to lay out some housekeeping rules. So please keep yourselves muted for the duration of the meeting. I'll give a brief overview of how today's session will look. And so shortly, I'll be introducing Salim and then handing it over to him for the main presentation. There'll be a Q&A session after Salim's presentation. To allow for no disruptions during the presentation itself, please send your questions directly to me in the Zoom chat. There's a host and panelist section as well. If you prefer, there's a QA section. If you can find that, that would be much better. I'll relay the questions to Salim based on the time we have at the end. If you haven't joined the IPN Slack channels, please reach out to me after the event, and I'll send you an IPN Slack channel, software engineering, community channel link. Also, you can follow the LinkedIn page. And now let's just dive right in. Let me introduce Salim. So Salim has approximately 15 years of experience in software development. He currently serves as a staff engineer at Google Brain. Google Brain is a research division at Google, investing in pure applied research with an emphasis on machine learning. He previously worked on programming language research for machine learning with Swift for TensorFlow at Google, and currently he works on computer architecture research with hardware and software co-design. He's been involved in porting Swift to multiple platforms, including Android, and is responsible for the Windows port of Swift. He has previously worked at Facebook, building both general purpose compiler toolchains and helped build a specialized domain-specific compiler for machine learning called GLOW under the PyTorch organization. Prior to that, he worked at VMware on their bare metal hypervisor, ESXi, as a kernel and system software engineer. Outside of his professional career, Salim also continues to contribute to a number of open source projects, including Swift and LLVM. He has previously been involved with GNOME and has helped maintain Linux distributions. He's been involved with a number of Jamaati institutions over the time and in different capacities, including AKEB and AKF, also now IPN. He is currently involved with AKF and serves on the National Council for the Digital Core team. So without further ado, I'm gonna hand it over to Salim. Salim, all yours.
Thank you, Yanlit, and thank you for the invitation to speak on the topic of conversational AI. Conversational AI is an idea that has been around since at least the 1950s. Alan Turing, in his paper, Computing Machinery and Intelligence, described what he dubbed the imitation game, a test where a human would interact textually with an entity and attempt to determine if it were human or not. The goal was to have the machine be indistinguishable from a human participant. The idea has kept a place in fiction. People familiar with Halo would recall Cortana, an artificial intelligence character. However, the implementation of the technique has become commonplace. Many of us carry the technology with us on our digital devices, or possibly have them accessible in our homes. Conversational AI is a subfield of applied machine learning with a variety of different domains. It requires both understanding language and synthesis of responses. This fits into a larger field of natural language processing. Modern computing technology has evolved significantly since Turing's time. The combination of increased computational power of today's hardware and the emergence of frameworks such as TensorFlow have made more ideas tractable. Many other areas, such as image classification, had breakthroughs more than a decade ago. Rediscovered ideas such as neural nets and improved data sets such as ImageNet were instrumental in helping image classification. Spurred by the successes of other domains, many companies are now investing in improving our understanding of NLP to harness the ability to understand and share ideas, thoughts, and requests with computers with the nuance, imperfections, and emotionality that language allows. I would like to describe some machine learning techniques and basics of language processing. We will flip back and forth between some fundamentals of machine learning and some of the recent breakthroughs in language processing. Hopefully by the end of this presentation, you will have learned something about machine learning and language and how they fit together. Linguistics is a complex topic, and that complexity results in a variety of subproblems that need to be addressed. In order to better understand the relationships, it can be helpful to understand a taxonomy. Natural language understanding, NLU, is focused on understanding language. This includes various things such as summarizing text or processing input to identify relationships between words. This is similar to what students may learn in grade school. They went to the store. We can identify a subject, predicate, prepositions, and an object. We can organize this in a hierarchical form, giving us the parse tree. The process of generating this syntactic understanding is called parsing. A counterpart to this is natural language generation, or NLG, which is interested in synthesizing language. You could consider this to be the flip side of the same coin as NLU. Composing a sentence requires one to consider more nuanced items, such as connotation, as well as objective things, such as synonyms, to avoid repetition. These selected words must be structured properly. Consider, I have this book to read, versus I have to read this book. NLP, or natural language processing, encompasses both. It includes tasks such as language translation within this domain. At the same time, there are a number of ancillary techniques that are associated with NLP. Being able to convert text to speech, to be able to respond back verbally, or to be able to process spoken words in a representation that the computer can work with are often required for handling human conversation. That certainly was heavy on computational linguistics, but there seemed to be a missing aspect. Conversational AI has artificial intelligence in the name, and where is that? Intelligence is the ability to acquire and apply knowledge and skills. This applies just as much to artificial intelligence. In order to imitate intelligent human behavior, the machine must be able to learn. Machine learning is a subdomain of artificial intelligence that is focused on learning from data rather than having to explicitly spell out an algorithm for every possibility. Within this domain, there's a specialization known as deep learning, which has gained popularity in recent years after it has been used in breakthroughs in computer vision. AlexNet, published in 2012 by Geoffrey Hinton et al. From the University of Toronto, demonstrated the use of deep learning for image recognition. The areas of language processing straddle all of these as it ties together concepts from all these domains. Computer systems have drawn inspiration from natural systems. The COVID-19 pandemic brought a term into vernacular, epidemiology, the branch of medicine dealing with the spread and control of diseases. One of the texts related to this, the Mathematical Theory of Infectious Diseases from 1975, served as inspiration for gossiping network protocols. Similarly, the human brain has served as an inspiration for ANNs, or artificial neural networks. This is an illustration of a neural network with firing synapses. Similar to the neural network of the brain, ANNs have networks of neurons which communicate with each other. Unlike physical neural networks, these are static and symbolic rather than dynamic and analog. While there is active research in building analog systems, known as neuromorphic computing, we are going to leave that unconsidered here. There are multiple ways to conceptualize the network, but one view is to consider a vector input being transformed by some function which provides an output. Each neuron takes its inputs and scales them by a learned weight, which we call the parameters, and applies a function known as an activation function, which is used to feed forward a value. Machine learning has a number of different approaches, each of which have a different trade-off. For the purposes of language processing, most learning approaches tend to be one of supervised, unsupervised, or semi-supervised. Supervised learning uses previously annotated data to learn. Someone has to identify whether the input is a dog or not a dog. This is used for training, that is, learning the weights associated with each neuron, which can then be used for inference, that is, applying the learning on other input. Unsupervised learning, unlike supervised learning, does not need to label data, but instead learns to cluster together similar data. Semi-supervised learning attempts to blend the benefits of both techniques. Unsupervised learning trains over part of the corpus, and the remaining can be labeled and processed subsequently. This type of learning can be useful in domains like speech recognition and text classification, amongst others. There are other forms of learning, such as reinforcement learning, which uses a model of rewarding proper execution, which reinforces certain pathways. This has practical application in things such as autonomous robots, but we will not be covering that here. Just as humans learn language, machines too learn from examples of the language. The difference is in the size of the corpora. Most models take what is equivalent to about 500,000 books to develop an understanding of the language. We must be careful about the data set beyond just the size. Overtraining, as well as training on a narrow data set, can prevent the learning from generalizing to new data, known as overfitting. I say modern here, as language processing has been a topic of interest to humans for a long time. One of the earliest instances of translating machine appears around 1930, and Germany's Enigma machine in the 1940s is another example of language processing. There were many previous techniques, such as TF-IDF, which is term frequency, inverse document frequency, which is quite popular in information retrieval and text mining. This technique would score the words in the document and the corpus to signify its importance. Logistic regression and Gaussian models, such as the naive Bayes classifiers, have been used in information retrieval. However, modern NLP techniques based on AI and ML are different in that they try to model the more complex relationships in language. Now we return to deep learning. Deep learning derives its name from the fact that it uses deep neural networks. Depth refers to the depth of the neural network. The length of the chain of transformations from the input to the output is the measure of depth. For feed-forward neural networks, this is simply one more than the number of hidden layers. While there is no standard threshold for deep networks, one of the early examples, which most would describe as a deep learning network, is from a fast learning algorithm for deep belief nets by Hinton et al. The general assumption is that there is at least one hidden layer. Convolutional neural networks, or CNNs, are amongst the most common neural network models. As the name implies, they involve a convolution, a mathematical term for a function which blends functions, or more simply, transforms some input. An example CNN here is Linnet-5, a computer vision model from 1998, which does text recognition. This is an image classifier, which gives an image with an output of a label of 0 to 9. The input is a 32 by 32 pixel grayscale image. The model will process this through 6 5x5 convolutional kernels with padding, reducing the image to a 28 by 28 matrix. Here, we will subsample the image, where we will average the neighborhoods together by an operation known as average pooling, which gives us 6 14 by 14 matrices. A second pass of a 16 5x5 convolution kernel yields 16 10 by 10 matrices. We again subsample with average pooling, this time reducing down to 16 5x5 matrices. Finally, a convolutional of each feature graph will yield a 1x1 value, which will be used to form a vector. This passes through 2 fully connected layers, which ultimately yield an output which classifies a value from 0 to 9, or one of the 10 digits. This process allows it to extract information both globally and locally to ensure that the structural information is not lost. Recurrent neural networks are different from feed-forward neural networks, networks which only pass data in one direction, in that they are able to have short-term memory by having data flow in a loop. Let us unroll the RNN on the left and look at time t. The neural network H has some information from the previous time step, t-1, forwarded to the next time step. This allows it to have some amount of knowledge from the previous step. This allows for context from the previous state to influence the next stage. This is helpful in situations where some information is more important temporally rather than spatially. Now, if you have noticed so far, we haven't really been able to remember much. The closest thing was the influence of the previous state in RNNs. Enter LSTMs, or long short-term memory. We can wire a historical input that crosses across cells and can be mutated and passed along in addition to inputs and weights. While there are many different models of LSTMs, the model here is the GRU, or gated recurrent unit. The unit combines a few layers and a few pointwise operations, which can update the running memory and provide a result. This allows for preserving some state across a RNN, which can be important in NLP, as language often relies on context from the surrounding portions. The realization that there is important context that needs to be maintained is a significant observation on how humans interpret language. When dealing with language, some bits of information are more relevant than others. At its core, this is the idea of attention, referencing the concept of cognitive attention from neuropsychology. By adding a concept of dynamic weights to encode the relevance of other content to the current aspect, we can more closely mimic language understanding. As an example, consider the sentence here. There is a certain degree of relatedness between eating an apple and between red and apple. We may describe them as the object of the verb and an adjective to the object. Attention models the relative importance of words to each other in a sentence structure, which can be important for processing the input. Sutskever et al. In 2014 introduced sequence-to-sequence learning models, which would transform an input sequence to an output sequence. This used an encoder-decoder model, where the encoder would convert the input into an embedding, a representation of a word as a vector, and the decoder would do the conversion and generate the output. Both sides were RNNs, employing LSTMs to perform the conversion. In order to address the limitation of memory, attention introduced by Banda et al. In 2015 set the stage for attention is all you need in 2017, which introduced some changes to the attention model and made it possible to do the sequence operations without RNNs. It introduced the concept of a transformer using multi-head self-attention, that is, multiple parallel instances of an attention-based algorithm. It could attend to further portions of the input and combine the encoding and decoding model from sequence-to-sequence learning. Imagine that most everyone here is able to tie their shoelaces. Now, if I were to hand you a segment of twine, would you be able to tie the two ends together? Again, I imagine that the response is overwhelmingly yes. However, is tying a piece of twine something that you're explicitly taught? I imagine not. However, your learning on a shoelace can serve as a starting point for this task. Transfer learning is a technique where a model trained for one task is repurposed for another task. It allows for the transference of knowledge from a related task that has already been learned. While this is not a specialized subdomain, it is a fairly common technique, and it is somewhat related to problems such as multitask learning and concept drift. There are some restrictions with this technique. Tasks need to be somewhat related. Additionally, it is important that the training data is sufficiently generalized, not only to avoid overfitting the model to the input, but to allow fine-tuning to new tasks. Assuming that the data set allowed the model to generalize well enough, we can add or remove layers near the edge and further train the model so that it may adapt the parameters for the new task. This retraining process is known as fine-tuning. When you have a model that you will fine-tune, you have two phases of training. With pre-training, we can train the model initially with the general concepts of the domain that we are interested in. This training is done with a large corpora and can be computationally expensive. The learned parameters can be subsequently used for fine-tuning, adding or removing layers of neurons at the edge, and then retraining with a smaller corpus targeted specifically for the problem that is intended to be used for. This allows us to start at a higher baseline and hopefully achieve the desired accuracy more quickly. The reason that this is an important technique is that there can be tens of millions of parameters that need to be trained, and the domain it may be targeting may not have sufficient amounts of data to train on, or the data may result in overfitting. The OpenAI GPT model builds upon the transformer and combines it with unsupervised pre-training. The vocabulary input is encoded using an older compression technique, byte pair encoding. This recursively replaces frequently occurring pairs with an unused character. Consider the word Mississippi. We can repeatedly replace the most frequently occurring pairs of letters, replacing SS, then alpha alpha, then beta beta, and finally PP. The model falls under semi-supervised learning, with unsupervised pre-training and supervised fine-tuning for the particular language task. In 1948, Claude Shannon, who is often called the father of information theory, published a paper, A Mathematical Theory of Communication, which laid the foundations of modeling the probability of a sequence of words occurring in a sentence, which is known as a language model. The GPT model uses a large corpus of unlabeled data and the decoder from the transformer model to build the language model. The language tasks are framed as prediction problems, asking the GPT model to fill in the blanks, which can be used for things such as language translation, question and answer systems, and even summarization. The input embedding is passed as input to the model's 12 transformer decoder blocks placed in a feed-forward layering, which produces a probability distribution over the target tokens. A rather interesting application in a revision of this model, GPT-3, was released as GitHub Copilot, an AI assistant which would provide code completion suggestions. The GPT model processed the input sequentially, processing input from left to right. However, language is not always so neat. Consider how the speech patterns for Yoda was designed. It required context from both directions. The BERT model sought to address this by using both left to right and right to left training simultaneously, stacking the transformer encoder to understand the language model. It uses two pre-training tasks: masked language modeling, removing some words in a sentence and predicting, trying to fill in the blanks, and next sentence prediction, predicting if two sentences logically follow one another. Pre-training on these two tasks allowed building a language model which encodes the syntax and the semantics of the language. A pair of sentences are masked and encoded with a tuple of token, position, and sequence encoding, which allows it to encode the word, location, and sentence. These are fed to the model, which generates a set of sequences which predicts the masked tokens, as well as if the two sentences are sequential. This semi-supervised learning is expensive, but allows it to create a language model. Subsequent fine-tuning of the model for the domain-specific task is less expensive and requires a smaller corpus. This leads us to Mina, a chatbot that Google AI revealed in 2020. Looking back at where we started, Alan Turing wanted to design a machine that would be able to converse in human language. This model provides such an entity. It is an open domain chatbot. That is, it is able to converse on any topic rather than being bound to certain keywords or intents. That is, identifiers and an input that hint at what the user desires. The generative model was trained on a corpus of 40 billion words and has 2.6 billion parameters. This model uses an evolved transformer model with 1 encoder and 13 decoder blocks. An interesting aspect of this model is that with even 2.6 billion parameters, the model can overfit with 40 billion words. Let me wrap up by first quoting Noam Chomsky. It seems that shortly before 50,000 years ago, some small group of us acquired the ability to take two concepts and combine them to make a third concept without disturbing the two original concepts, without limit. What paleoanthropology teaches us is that humanity acquired the ability to describe things in a way that is intricately linked with language. Language allows us to describe things, and descriptions allow us to tell stories. It is storytelling and understanding stories that enables knowledge transfer. But language also allows us to control perception and to imagine things that we may not have experienced. This is one reason that why language processing is so intriguing. It allows us to understand how humans think. Recent breakthroughs in machine learning have reignited natural language processing research. While there have been a number of breakthroughs, there is still a lot left to discover. There are new techniques and applications of the technology being developed. Hopefully, this has given you a small vocabulary to understand the ideas and build new experiences with, or perhaps even find the next breakthrough in NLP. Thank you.
Awesome presentation. Thanks for that, Salim.
Thank you.
All right, so again, thanks for the presentation. Very informative. I'm going to open the floor for some Q&A. So I have been receiving a few questions via Zoom chat and the Q&A block. We'll begin with those, and then if anyone still has any questions, feel free to continue to send me the questions via the Q&A feature in Zoom or via the host and panelist section. I'll be monitoring both and then asking questions to Salim. So if you're ready, Salim, I can kick it off with some questions.
Sure.
Cool. So the first question we have here is, how much storage differential is needed between long-term and short-term memory? I think it's around space complexity that's needed in both.
So for LSTMs, it's normally you're keeping it in memory, right? It's not that it's necessarily storage in terms of like disk storage, but more in memory, and it depends entirely on the amount that you're trying to remember. So you can scale that as appropriate to the model that you're building.
Awesome. Cool. Another question we have is, so what is the biggest jump in transfer learning that you have seen which works without fine tuning? I guess the question is asking, in your example, oranges to lemons, shoelaces too. So what's the biggest jump you've seen without any fine tuning?
I would say that one thing that has really surprised me personally has been the GPT model with with GitHub's implementation. It's really been very, very exciting to see how it can learn from arbitrary languages and then reapply it to different ones. A really good example was it's obviously had some input from some C# input for the .NET runtime, and it's able to actually synthesize code in Swift and C++ just fine. So it's really fascinating to see how that works and how it generalizes.
Yeah. I think just to add in there, like I've seen a crazy jump with, or I've heard about where, you know, when you mention language, I think Google Translate, the ML invented its own intermediary language, right, in between. So that's pretty impressive, I would say.
Yeah.
Okay, this is, I think, more generic. For someone looking to enter into ML, what recommendations would you have?
I would say that there's a few things to consider. One of them is sort of identify what area of machine learning you're actually interested in. There's so many applications, and each one has its own sort of specialized language and just background information that you would need to learn, right? So once you have identified that, just really dive in. There's a lot of resources available all across the internet. Papers are an excellent source of information as well, so arXiv is always good for that. The other thing is there's a ton of open source projects. You can always learn practically. Again, this depends more on the person. Some people learn better practically, some learn it through just reading. And so look at what works better for you and then choose between the two, right? You can work with open source projects on the side often and gain a lot of knowledge that way.
Makes sense. Yeah. For me, I feel like I'm more of like a hands-on learner. Definitely have to go through the tutorials and learn things, especially with, you know, concepts like coding and stuff. I think those are more hands-on, right? For sure.
Yep.
All right. The next question is, how do you find good data to use to train your models, and how much of your work becomes data sanitation?
Yeah, that's an interesting question because the data input is very, very important, right? And so I think it depends on the tasks at hand. Many of these domains have started building up data sets that can be used. And that's usually a good starting point, I think, because you have the collective power of multiple people and communities coming together and sort of adding in different types of data, sanitizing it, and trying to make sure that it's varied enough, because that's absolutely critical, as I mentioned, right? Like overfitting and overtraining can result in the data in the model just being too narrow.
Makes sense. Yeah. I think, yeah, data is very critical when training these models, right? So it's probably like a critical component. Okay. I think, again, very generic question. So what skills do companies look for when hiring software engineers in the AI ML domain? And how can someone better prepare themselves for it?
I think that's dependent very much on the company. Hiring processes are pretty contentious. There's, you know, the general way of preparing, I guess, is the usual, right? Like make sure that you brush up on fundamentals and sort of understand the concepts. Being able to apply them is usually the biggest thing, right? So if you're looking at, say, language processing, it makes sense to understand transformer models since they're so popular right now. They're really near the cutting edge. So understanding sort of the domain-specific bits would be a good way to prepare for that. And in the process, I imagine that you would actually brush up on all of the necessary background that you'd really need for that.
Right. That makes sense. I think along the same lines, the next question is, so what skills can software engineers leverage from their present role to get into the AI ML field? I think this is very generic. I think when they're referring to software engineers, maybe I would answer this and take it from a lens of like maybe like front end full stack engineers, right? What can they take from there? Because software engineering is such a broad spectrum. So yeah. I think the majority of our Slack group is like, full, either front end or back end engineers. And ML is such a specific topic. So let's approach it from that angle. So how can a full stack developer leverage their present role to get into the AI ML field?
Right. It can be dependent on sort of, the situation, but I'd say that there's a lot of skills that transfer fairly well, right? I guess it depends sort of on where the focus is. If you're focused more on model building, there's the whole thing of sort of understanding the system, right? Understanding how things come together, how they interact with each other, how to sort of diagnose and isolate things. So the normal debugging techniques, right? That type of stuff can be very, very helpful and directly applicable. If you're looking more at it from the infrastructure side, again, that's again, in some senses, more full stack as well, right? Like you need to understand how both sides are going to interact and come together. So there's the general engineering aspects that apply very well. And it's usually, there tends to be some bias towards people who are lifelong learners when coming to software engineering, and that type of mental model works really well for this.
Sense. Just another question that we got in. So one of the biggest challenges someone sent in that they found was translation of, like German reviews, so one language to another. The question boils down to, why is translation and transliteration still a hard domain to solve?
I'd say that, there's difficulty that comes in just from the nuance of language. There's idiomatic usage of language. There's just daily vernacular that gets thrown in, and you need to be able to find a model which encompasses both of them. And a way to think about it, right? People have differing levels of ability to speak, right? And to sort of process a particular language. Some people don't understand English at all, others are fluent in it. And so you're trying to build up a model that can understand a variety of different languages and speak them all equally well. That is inherently difficult for humans, let alone machines.
Yeah, agreed. I mean, it also boils down to, just semantics and ordering of things as well. It's sometimes some literal translations just don't work out of the box.
Yeah.
Okay, the next question we have is very generic. See if you can answer this one. Hard one for you. So do you have any open source libraries that small businesses can benefit from?
To be honest, I don't really track, all the libraries out there for this. There's just so many.
Yeah.
I would say that if it's businesses looking into it, they're more likely looking for more of a end-to-end solution rather than just a library to build something. Because if you're building this from scratch, right? Like, what level are you doing? Are you planning on building up the model, training the model, deploying the model, and then sort of layering layers on top of it? Or are you looking for something to just interpret it? And so end-to-end solutions, I'm not as familiar with. One that I do know of that comes to mind is, I believe, Dialogflow by Google, which sort of which has a lot of the pieces, including one of the models that we talked about, BERT, sort of packaged up where you can actually use it to build up, interactive chatbots.
Yeah, I think at least for that question, I think there's multiple ways, right? Like when you talk about small businesses, there's many different ways. I feel like building out maybe like just a whole model or just the ML wouldn't make sense. I feel like a small business would probably like lean on something like have you seen the Facebook chatbots? Like they have pretty good. I've seen a demonstration where people have integrated like WhatsApp and Facebook Messenger chatbots with Google AI to drive the back end. So that's been cool. So I feel like, it's better to leverage more of like what exists out there for like small business. So I guess we have probably time for 2 more questions. So can Mina be integrated with an existing application?
I don't know off the top of my head if Mina itself can directly be integrated. The idea is, though, it is a model. There is a paper on it. I don't know if the implementation has been released or not, but the learnings from it could be applied, and someone could definitely, try to rebuild a model similar to it and integrate that. Of course, there is the amount of work that needs to go into that.
Okay. And then I like this question. It's the very last question. It'll I guess keep everyone thinking going forward. Very open-ended. Can you talk about how you see software engineering, testing, product development, AI evolving in the next 10 years?
If only I had a crystal ball. I think that, we've seen a lot of growth and changes over the years with tooling getting a lot better.
Right.
And I think that that trend is likely to continue. New tools, new techniques being continually brought up, and just changing the way that we approach problems, and just learning from what we've actually already accomplished, right? Of course, there's also the other end of this, which is hardware is now becoming a problem with Moore's law sort of slowing down, and Dennard scaling slowing down as well. So we're going to rely more on this hybrid approach, right? You need to both understand the software and have special purpose hardware that will help accelerate things, sort of bring together the domains and push forward that way. So there's a lot that'll come up, for software engineering to solve problems much more collaboratively.
Agree. When you talk about the hardware being a limit, I don't know if that's that's very true. Have you seen the new M1 and M2 chips from Apple? Those are like through the roof performance with ML.
Yes.
So I guess we're not stuck there for too long in the hardware space. And then, yeah, so I guess that was our last question. But before we end, I want to thank you once again, Salim. Thanks for your time and your seva for helping the Jamaat understand AI. Thank you everyone for joining. You guys can stay tuned for more events on our Slack channels and LinkedIn groups. I had pasted the links earlier in the chat, but I can send them again. And I see one question about needing to be invited to the IP and Slack workspace. I don't think so. I think you just need to make an account, join with the link that I sent. And so you can just join into that. And then feel free to, reach out to me. I think we have more logistical questions. Do we have an AI ML group for IPN? I think it's data science. But if you're talking specifically AI ML, I don't think so. You can browse through our channels list. So each community has a channel per se, but I think our software engineering community is the broadest one that we have. So it covers AI and ML should be covered there. You can always post a chat there, and if it needs to be redirected to like the hardware group or something, I can always assist with that. But thanks everyone for joining again today. Thank you, Salim. And thanks everyone. Have a good rest of your weekend.
Thanks, you too.